Okay, folks, welcome. So today I'm going to actually go over a lecture I gave earlier today on dimensionality reduction using PCA. And before I do that, I just want to give a shout out to James and Sammy from the Discord who saw an early version of this and whose feedback was really useful. So I spent this morning actually, based on some of that feedback, kind of rearranging some of the stuff in this presentation, and I think it really improved it. So thanks to those guys. And yeah, I hope you guys enjoy this. It kind of covers much of the same material we've been covering in chapter 12, the early parts of chapter 12 in Bishop, so there'll be a lot of overlap there. But I'm going to kind of introduce it from um, a more, I guess, basic level, so kind of build up everything we need as we go. So it doesn't assume PRML levels of knowledge. I'm gonna try to introduce all the terminology that we need. So see what you think. Okay, so here we go. Dimensionality reduction using PCA. So, why are we doing this? So I gave this talk to a neuroscience audience, and in neuroscience, the data that people deal with is very frequently high dimensional. So, for example, in this particular case, let me get the laser pointer out. So we've got the responses to about 40 odors of a population of 150 neurons. So you can imagine each one of those responses, each odor responses, is a point in a 150 dimensional space. And somehow we want to kind of deal with that. We want to kind of visualize it, get a grip on it. So one motivation is just trying to deal with the high dimensional data that exists in neuroscience. So when we want to visualize this data, then frequently, well, I mean always, we need to project it down 2 or 3 dimensions. And how do we do that? Now, one way you could do it is you could just plot, let's say, the responses of the first neuron against the fifth neuron. And here I've colored, so each point here is now corresponds to the response to like one odor. And I've colored them based on, what odor it is. And you can see, okay, there's just kind of some smattering of activity. But why are those two neurons the ones to choose? You've just kind of, the experimenter has, inserted an electrode, picked up some neural activity. Why are those particular neurons the right ones? Well, whereas PCA says that actually there is a kind of a principled way of picking directions of activity in space that, by some exact measures, actually capture most of the action, and we can kind of make that statement precise. But you can see that even during applying PCA to the data that we have, it already seems to have separated these kind of red odors from these blue odors. Found some interesting structure in the data. Whereas here, I mean, it's unclear what's going on, and it's kind of unclear why you would pick these two cells. Whereas in PCA, we can actually kind of justify our choice of these kind of principal components, and in some sense say they're kind of the best ones to pick for if you need to project the data in two dimensions, 3 dimensions. The first, however many principal components, are the best ones to pick. Another perspective is kind of the one that's quite current in neuroscience these days, that the high dimensional data that we see, those 150 dimensional response vectors, they're actually coming from a lower dimensional manifold that's been kind of embedded in this high dimensional space. So, for example, here's kind of the very famous kind of Swiss roll data set, where you've got points that are living in 3-dimensional space, but actually they're coming from a 2-dimensional surface that's been kind of embedded in 3D space. And PCA can help find those those low-dimensional surfaces as long as they're restricted to be kind of linear. So lines, planes, hyperplanes. More complicated shapes like this can't be really picked up by PCA, but there are extensions like Kernel PCA that do handle that, which we'll touch on at the very end. Another motivation is that of denoising or data compression or approximation. These are all kind of very similar things. So here's again our original data matrix, and there's a lot of structure there, but it turns out that we can actually approximate it if we use the first 2 principal components pretty well already, right? So the number of components we would have available in this case would be about 48, the smaller of these 2 numbers. But using just 2 components plus the mean allows you to capture lots of what's going on, a lot of this structure. So one interpretation is that actually, well, all of this additional salt and pepper patterns are actually noise on top of this low dimensional structure that we're finding by trying to find 1 or 2 or 3 dimensions in space that capture the variability we're interested in. So that's kind of yet another motivation. And now how do we do all of that? And the key idea behind PCA, there's actually, several ways of getting at it, but one approach is to say that, we want to find directions in data space, so in that 150-dimensional space, that maximize variance. And so we're going to talk about, in this talk, we're going to talk about, what we mean by directions and, what we mean by variance and, why is maximizing that a good idea. Okay, so we'll try to answer some of these questions as we go. Here's kind of an example that I got. I think thanks to Sammy for the heads up about this. This is coming from CS229. It's a Stanford machine learning course. So, the idea is we can look at it. We've got, 5 data points, and we can, the data arrives with these coordinates. But what PCA wants to do is try to find, look, we want to summarize this data in one dimension. Well, how do we do that? Well, we try to find a direction in space where if we project the data onto that direction, so we get these points, it captures most of the, most of the variance. So this seems like this is a pretty good direction. This other direction, again, is not great, right? Because the projected points seem to kind of get squished. So as long as you buy that, maximizing variance is the right thing to do, and we'll see an example at the very end about a situation where it might not be the best thing to do. But, a priori, I think it's not a bad idea to capture most of the energy of your signal. Then you want to find directions that maximize that, and PCA will try to give you this direction. So the question is how we find this. Okay, so kind of the outline of the approach. So what we're going to do is we're going to talk about the notion of variance and look at it just, variance is a property of, scalar of, one-dimensional signals of neurons, neural activity. And we're going to talk about the variance of single neurons. And actually before that, and the key idea is we're going to talk about single neurons as coordinates in that high-dimensional space. And then we're going to look at how to compute the variance of single neurons and the covariance of neural populations. And then what we're going to do is we're going to revisit this idea of the variance of single neurons, but from the kind of population view. So say, look, actually, how can we relate, instead of viewing this neuron as in isolation, how can we view it as some kind of a projection of the overall covariance? And once we've got a handle on that, then it's actually a very simple step to then consider coordinates that don't correspond to single neurons, but then can correspond to kind of combinations of neurons. And essentially to define a new coordinate system consisting of those combinations. So these coordinates will then find these kind of pseudo-neurons that are they're not actual neurons that we've recorded, but they're combinations of neurons that are maybe more useful for trying to understand the structure of our data. And then we'll show that computing the variance of pseudo-neurons is exactly the same as doing it for single neurons, with just a slight change. And so once we've done that, then the idea of PCA is to find these pseudo-neurons that have kind of the maximum variance, right? So our search becomes, how do we do that? How do we find, we can compute the variance of any given pseudo-neuron. How do we find the one that maximizes the variance? And that's where we talk about singular value decomposition. So first we'll touch on some basic facts about matrices, and then we'll describe what the SVD is, a singular value decomposition, and then we'll use it to find the maximum variance direction. So essentially to read off the maximum variance directions. And then we'll have a little application to neural responses at the end, and I'll kind of finish off by talking about adjacent approaches, how some extensions you can think of PCA that you can apply if let's say you want to use nonlinear techniques. Kernel PCA is the one to use. If you want to compare two different data sets, CCA is the one that you want to use. LDA is for the case when you have labeled data. Here we're in kind of an unsupervised setting where the data is unlabeled. But what if you have labeled data? Well, then maximizing variance is not the thing you want to do. You want to maybe maximize discriminability, and in that case, there's kind of a related linear technique called LDA, which does that for you. So we'll just touch on those at the very end. Okay, so let's start with the variance of single neurons in the first instance. Okay. All right. So notions of dimensionality. Before we kind of get into dimension reduction and all of that, let's just talk about what we mean by dimension. So we saw this Swiss roll example. And Swiss roll example has kind of an extrinsic dimension, which is the dimension the data arrives in. There's 3 dimensions, but we can see that it lives on this kind of low dimensional. The data actually is coming from a low dimensional set. And this lower dimension is happening because there's kind of correlations in the data, right? So if, if neuron 1 goes in one direction, and neuron 2 goes in another direction, well, neuron 3 is no longer free to move, right? It has to move in such a way that it stays on the manifold. And that restriction, that correlation between them, is kind of what's producing this lower dimensionality. And so PCA tries to find, again, as we mentioned, this kind of this lower dimension, but it requires it to be linear. So it can't find stuff like this. It can only find kind of lines or hyperplanes in this particular case. But it's trying to find, it's think of it as kind of a simpler example of algorithms that can find these complicated manifolds. It's trying to find an intrinsic dimension that's linear. Okay, so the next. All right, so now we're going to talk about kind of the importance of coordinate systems. Our whole approach to this problem of finding directions is going to be based around having the right coordinates. Now, as you might know, so one of the big realizations of 20th century physics was this notion that the laws of physics, and I think probably even 19th century physics actually, was that the laws of physics shouldn't depend on your coordinate system, right? So it shouldn't depend that you're using polar coordinates versus I don't know, Euclidean coordinates, right? The physical laws should be the same, and they developed a bunch of machinery that allows them to express the laws in just that way. Now, neuroscience, on the other hand, it depends on having the right coordinates, right? And so, the input is coming into, let's say, to your eyes along, let's say the pixels in your retina. But those, those raw pixels aren't necessarily the right ones with which to, let's say, find whether there's a dog in front of you. And so you have to kind of transform your data into a right coordinate system, which makes those kinds of decisions simple to do. And so you can think of what happens in the visual system as essentially progressive transformations, such that at the very end, it actually becomes how you arrive at coordinates in which the decisions you care about are very simple to make. So, the coordinates that you have, you need to have the right coordinates, and those aren't necessarily going to be the ones that your data is recorded in. So PCA tries to kind of find right coordinates and essentially find coordinates that are kind of matched to your data. So your neural recordings might arrive in kind of neuron 1 versus neuron 2. That's just what you happen to record. It would be amazing that if those two neurons were just the ones to be looking at. But PCA tries to grab that data and find directions in it that are better matched, that describe it better somehow, by finding directions that seem to capture most of the variance. This is the most, and then, well, in this 2D, there's only one other possible direction. But if you have higher dimensions, then you find the first most variance-bearing dimension, and then the second most that's perpendicular to that one, and so on. So you find coordinates that are suited to your data rather than coordinates that just your data happens to arrive in because that's what you just happen to record. Now here are kind of the standard coordinates, that your data arrives in, right? So again, this is actual responses of 150 neurons to one of the very first odors. So these points correspond to the elements of that 150 dimensional, vector that represents this population, the response of the whole population to this one odor. Okay, and now what I want to get across is that notice that we have some implicit coordinates here, right? When you write this population vector, we can actually write it as some amount, x1 of the first neuron of activity in a direction that is specified by the first neuron, x2 in the direction of the second neuron, and so on, right? So just like in this picture where we say, well, this point is actually some amount times the first neuron plus some amount times the second neuron. That's exactly what you're doing here. You're saying my coordinates correspond to the activity, one unit of activity of a single neuron. So let's write that. So for example, E1 is the vector will be 1, 0, 0, da, 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 da. E2 is 0, 1, 0, 0, da, 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 and continuing in that way. So each coordinate is corresponding to the activity of one neuron. And we can build up, the whole activity vector in that way. Now these coordinates have a special, some special, they're probably obvious properties. But this coordinate system that we have of activity in terms of, individual neurons, it's complete. So we can represent any activity vector that involves those neurons in that space. That seems quite obvious. They're orthonormal, which has two parts. So the vector, the basis vectors that correspond to one neuron are they're orthogonal to those for the next neuron, right? So just like what we had here in this picture, neuron 1 is perpendicular to neuron 2. They could, in principle, do independent things. In real life, they won't, but in principle, we could record activity in neuron 1 independently of neuron 2 and just put it down. And finally, we have this kind of normality property that they're these unit vectors in those directions corresponding to activity of neuron 1, neuron 2, etc. They're of unit length. This is an orthonormal coordinate system. It's just probably the standard coordinates that you would think of. But the key point is that when you record activity like this, that's coming in with implicitly with this coordinate system in terms of neurons. Now, how do we extract single unit activity from in this framework? Well, you can think of extracting it as projection. So let's just focus on the first two neurons, and if you look at the data, this is kind of what they're doing. So this should say neuron 1, neuron 2. Neuron 1, neuron 2, doesn't matter, the labels don't matter. But the whole point is we get the point in two-dimensional space now describing these two neurons, and we just project to get the activity of the first neuron and project to get the activity of the second neuron. So we're taking this population vector, projecting onto the direction that corresponds to the first neuron, projecting onto the direction that corresponds to the second neuron to get their activity. This is exactly, this is the natural thing you're doing anyway, right? If I gave you that this was the activity of the population and you want to know, well, and I asked you how much is neuron 1 firing, you would just look at the axis, right? Well, what does that mean? Well, you're dropping a line to that point on the axis and reading off the number. You're dropping a line to that point on the y-axis, reading off. That's what you're doing. You're projecting onto the corresponding unit vectors. Okay, so that's how we get a unit activity from the population. And we write it in this way. Okay. Now, how are we going, once we got that unit activity, how are we going to kind of summarize it and capture it? So here what I've done is, this is X. We've looked at the activity of neuron 1 in response to all of the odors. I index, if you see any Greek indices, that indicates the stimuli, so the different odors. So there should be about 48 different dots, colored the same way I color the odors. And here is, the activity. So some odors are very exciting, some odors are quite inhibiting. And the question is, how should we summarize the activity of this neuron? We're talking about finding direction that kind of capture the activity of a neuron. Well, how should we define that activity? How should we summarize it over, a population, a set of odors? So one obvious possibility is to just use the mean. And look at how, so all we do for the mean is we sum over stimuli the responses of that neuron to that stimulus. And then we divide by the number of stimuli. It's just an average, right? And so whenever you see these curly brackets, these crooked brackets, that means it's an average over stimuli. So I take the activity for each stimulus and then I average over all the stimuli. Okay, and that's fine. That is one good way of doing it. The problem is that this neuron, for example, seems quite active, and yet it has positive and negative values. And so if we just computed this activity, then the mean, it might end up being close to 0, even though the neuron itself is actually quite active. So the mean is probably not what we want for that reason. If we could guarantee that the activity was positive, then maybe that would work. But in general, we want to keep it around, but maybe it's not the best measure. We could take kind of the absolute value. Nothing wrong with that. Take the absolute value relative to the mean. And that's kind of important because, like if there's no deviation relative to the mean, maybe you've got a neuron that's like not even responding to your stimulus, right? So, for example, maybe that neuron is just like holding your head up while you're smelling these things. So it doesn't actually care what the odor is. So the mean activity is high, but it's not being actually, there isn't variability caused by your stimulus. So it's not really responding to your stimulus. So this kind of idea of deviation relative to the mean is probably a good idea, but how should we evaluate that? Should it be the absolute value? Maybe we should just take the squared value. Forget these deviations, just take the squared values. So the measure we're going to use is going to be the squared deviations, the average squared deviation, also known as the variance. And now we talked about why we want the average deviation, because again, we want to capture effects that are actually responding to our stimulus. The squaring, that's one of the key justifications is mathematical tractability. It means we can actually do things, we can find things in closed form. Seems to work well often in practice, but it does have its problems. So for example, it's quite susceptible to outliers. So let me move this out of the way a bit. So here I've plotted the order responses of a neuron, and then I've computed the deviation from the mean, the absolute deviation, and the squared deviation. And you can see that, okay, well, obviously when the responses are small, it doesn't make much of a difference. But when you get very large responses, the square deviation weighs them, quadratically. So they end up being quite influential. Whereas in the absolute value, they contribute, yes. A deviation out here is quite large, but maybe it shouldn't be weighted so much. So there are very good reasons to actually prefer maybe a measure like this, and in fields like robust regression, they actually do use measures like this rather than the squared deviation. But because of mathematical tractability, we're going to actually stick with this, with the variance. Okay, so that's the measure of activity we're going to use. Average squared deviation relative to the mean. Okay, so we're going to use a variance, but neurons aren't going to be responding independently, right? They're frequently going to not just vary, but covary. So again, these are, now I got to move this out of the way. So again, these are, I went and looked at a data set, looked at neurons, a pair of neurons, real neurons, whose activity is covarying in a negative sense. So whenever the activity of one increases, the activity of the other comes down. Now here's a pair of neurons for which there's no relation. There seems to be kind of no obvious relationship between the activities. And here's another pair where the activity is actually increasing. So they're covarying in the positive direction. And so now we have a notion of covariance, which tries to capture things going up and down together. And what we do is, we take the deviation of one neuron from the mean, and we multiply it with the deviation of the second neuron we care about. And why do we do that? Well, essentially we want to capture things going up and down together. So if this deviation is positive and that deviation is positive, so the two things are going up relative to their individual means together, then the product will be positive for that odor. Conversely, if they're both going down, this will be minus, this will be minus one, we'll get, again, a positive contribution to the covariance. And so when we average that over the odors, then we'll get maybe something like this, a positive covariance, like what we're seeing there. On the other hand, if they're going down in opposite directions, this will tend to be positive when this is negative, and vice versa. So we'll get a negative number. So we'll get kind of a situation like that. And finally, if there's no relation between them, then we'll get positive things going up and down together as often as we'll get things going in opposite directions. So this number will be 0. So that's kind of covariability. And actually, interesting, it turns out variance is actually covariance of a neuron with itself, right? So we had the square term, we can actually think of it as the square deviation, of the covariation of a neuron with itself. That number will always be positive, reflecting the fact that, the variance will be a positive quantity. But so you can think of, variance as a specialization of covariance when the two arguments are the same. Now, once we've got that, covariance information, we can put it into covariance matrix. So that's what it looks like. Covariance matrix is just a big table of numbers. And this is covariance of x1 with x1, which is the variance, x2 and then x2, which is the variance of x2, so on. But the off diagonals have the covariance of pairs of different neurons. So you can see that structure like that. Another way to write this, and we won't go into why it's actually written this way, but we can actually write it as the outer product of the difference of in an odor response from the means with itself. And the only reason I put this up here is because later on, I just want you to recognize when this pops up in some equations. But yeah, the key idea is that it's just a table of the covariances. And here's kind of an example of it for, again, a neural data matrix. So what we've seen before, cells, odors, I've rearranged them so that the cells that are more active tend to be on the right. Now we compute the covariance, and this covariance is 140 something by 140 something, right? Because that's how many neurons we have. And now notice that this early block of covariance is very small because corresponding to the relatively small activity that's going on for those first early neurons. As we go farther along, you can notice the variance is increasing, corresponding to the fact that we're getting more and more active neurons. But also we're getting some interesting kind of block structure, right? So we're getting, for example, it seems to be kind of a block of activity there, corresponding to the fact that we have neurons that are responding, but that their responses are kind of similar, right? So like the first couple there, for example, seem to like this odor and this odor, and maybe a little bit of a preference to those intervening odors. So they'll get kind of a large covariability, and that'll contribute to getting this, this big block of, showing up in the covariance. This big block of activity showing up in the covariance. It's also indicating, for example, that this neurons over here are maybe covariant with some of these ones at the end, right? And that's kind of what this structure is. So it kind of tells you both the strength of the responses along the diagonal, and also how much that strength is distributed in covariation with the other units. Now it turns out that actually this covariance matrix isn't just useful for bookkeeping or doing pretty pictures, but it's going to be key to this whole notion of finding these maximum variance directions. So we're going to see how to do that by talking about the notion of pseudo-neurons. Okay, so we've been talking about neurons so far. Let's switch to talking about pseudo-neurons. And let's see where we're going. So, PCA is about finding directions that maximize variance, right? That's kind of what we've said from the beginning. Now, the standard coordinate directions correspond to single neurons, right? That's kind of the directions in which we get the data. The data arrives at that. The variance of single neurons is variance along these directions, and we'll see that shortly. So, the variance of that neuron is going to be the variance, the covariance along that direction. We can define other directions as pseudoneurons. And the variance of pseudoneurons is going to be, we should actually be writing covariance, the covariance kind of projected along those dimensions. So then PCA is then going to be finding the pseudoneurons with the largest variance. So we're going to see how, we can actually think of the variance of a single neuron in a slightly different way, from a kind of population level, as a projection of the covariance along a particular direction. And then we just play the same game for arbitrary directions, which define pseudoneurons, and then we just find the directions in space which maximize the variance. Okay, so let's look at the variance of a single neuron again. So previously, we just took the data for x1 mu for neuron 1, right? That would be the response of the neuron to all of the odors. Now this is just projecting the population vector along the first coordinate. We talked about that, right? So then, if we want to compute the variance, we have to compute the mean. And it turns out that that's actually just a projection of the population mean onto the direction that defines this neuron, right? So remember, this is what this direction defined neuron 1. We wanted its activity, so we projected the population vector along that direction. We wanted the mean activity, so we projected the mean. Now we're projecting the mean population vector across that direction. And now let's compute the variance. So we just put in the formula, so deviation squared, there shouldn't be a tilde here. And now we're going to plug in, well, how do we compute this? Well, we project the population activity onto the first dimension, and we subtract the mean, which is a projection of the population mean onto that dimension, right? So then we can just combine, we can just do everything in population space first, subtract the mean in population first before projecting. And then it turns out, well, this square, we can rearrange this square, the squaring that happens, as, well, this once, there it is, and then putting it twice, but we can flip the order, so it looks like that. And now because the direction that defines the neuron doesn't depend on our stimulus set, well, we can just pull out these components. And what is this? Just the covariance. So you don't have to kind of follow every single step with that, but the point that I want to really get across is that to compute the variance of just a normal neuron, we take the population covariance and we project along a direction that corresponds to neuron 1. Okay, and we've done this, so now we've done this projection multiple times. We wanted the activity, we projected the population vector along that direction. We wanted the mean activity, we projected the mean of the population vector along that direction. We wanted the variance of the activity, we projected the covariance of the population along that direction. Okay, so the variance of neuron 1 is covariance along its direction. That's the way to look at it. Why do you want to look at it this way? Because it's going to free our mind from being tied to these single neuron coordinates and to allow us to look at arbitrary directions in space. Okay. So let's get into looking at those other directions. So other orthonormal coordinates define pseudoneurons. Okay, so previously we described the population activity in terms of standard coordinates E1, E2 of neurons. Remember this, right? So we said the population vector is some amount of activity of neuron 1 plus some amount of activity of neuron 2, etc. Now, we can equivalently describe the same activity in other orthonormal coordinates. And these coordinates are going to define the pseudoneurons. So what do we mean by that? So here is the activity, again, focusing on the first two neurons. It is some amount. And now, this is the origin. And that position corresponds to, whatever, 125 and, 150. So that's the response that we observed. And notice that the axes here are the activity of neuron 1, activity of neuron 2. But we don't have to use those directions, right? We can define a new pseudoneuron that is a combination of E1 and E2, maybe some of E1 and E2. And then another one, E2, which is perpendicular to that one, so it corresponds to, some decreasing activity for neuron 1 and increasing activity for neuron 2. And we can still express this activity in those coordinates, right? So if we kind of shift our head, we twist these over and we look into now the activity of the pseudoneuron, well, this position, that response now is sitting over here. But it's clear that, in these coordinates, we can still capture any activity. It's just that the numbers will change. So now, pseudoneuron 1 has a lot of activity and pseudoneuron 2 barely has any. Okay, so this is again, so we can, we have orthonormal coordinates, so unit vectors in these directions perpendicular to each other. They're complete. We can capture anything that's happening in two-dimensional space, but the numbers will just change. Okay? So that's kind of this notion of pseudoneuron, directions in space that are combinations of the neurons we've actually recorded. Now, how do we do this activity and variance of a pseudoneuron? Well, it's exactly the same thing, but we just change the direction, right? So let's say a pseudoneuron has a direction U1. Well, the activity, how do we get it? We project the population vector along that direction. How do we get the mean activity? We project the population mean along that direction. How do the variance? Exactly the same computation. We project the population covariance along that direction. So it's exactly the same pattern, right? So the variance of pseudoneuron is covariance along a particular direction. So once you follow this pattern, the variance of any pseudoneuron, you just give me its vector, I'll give you how much variance it has, where I project onto the covariance. So now that's awesome because PCA now becomes finding the U, the direction, that maximizes this variance. But how do we do this? So it turns out, you can do it by calculus, but it turns out that we can actually do it in kind of one go by decomposing the covariance matrix. Okay, so before we get into that, let's just cover some basic facts about matrices that we'll need to answer this question. Okay, so here are some matrices we've already encountered. So this is kind of the data matrix. It has 40, 45, 48 odors, 150 neurons, a rectangular matrix. Here is a covariance matrix, a square matrix of 150 by 150 neurons. So data matrix rectangular, covariance matrix square, symmetric. You should ask, why is it symmetric? You should understand why it's square, and you should ask yourself why it's symmetric. So why is it that covariance of x1, x2 is equal to covariance of x2, x1? It's not a trick question, but make sure you understand why that is. Okay, so now let's look at a few different ways to view matrices that we're going to need when we're talking about singular value decomposition. So the standard way we're given is as just a table of elements. But you can also view it as a bunch of stacked rows, right? So you can think of like this becoming that, this becoming that. These are vectors now, and just stacking them on top of each other. You can also think about it as, stacked columns, right? So like taking this, that's there, taking this, that's there, and so on. Right? So 3 different ways. And we're actually going to find that both of these ways are going to be very useful for describing what SVD does. And then from that, being able to do PCA and reading out the answers we need. Okay. Now what do matrices do? So once we have a matrix like that, what does it do? So the idea with matrices is that they linearly transform, n-dimensional inputs, whatever n is, into some m-dimensional outputs. Okay, so it's kind of a machine that produces very simple transformations of inputs in one space to outputs in another space. Now we can think of this operation, and this is kind of how it's defined element-wise, right? Like you take all those elements for each row, you do this kind of, this multiplication, and it's all kind of dull. But you can actually view it in step back, so instead of focusing on, these exact details, you can actually view it from 2 different perspectives, from the rows and the columns. One of these ways is you can think of this as the analysis perspective. Right? So what are we doing? When x comes in, we are projecting x onto each of the rows. We're kind of analyzing, we're trying to break it down and say, well, how much does overlap onto this much? And how much does overlap onto the second row? And how much does overlap onto the nth row? You can imagine these ones, for example, being those standard basis vectors, right? So it says, okay, this guy's going to grab the first part of x. This part's going to grab the second element of x. This one's going to grab the mth element of x. So we're extracting parts of x and storing the result. Another way you can, think of it, another example is like, imagine if x was a sound wave and these R1s and R2s were filters that grabbed like the bass component, the treble component. So this would be, let's say, the 1 Hertz component. I'm going to grab that part. I'm going to grab the second 2 Hertz component all the way. So we're analyzing, we're breaking down x into its parts. That's one way, using the rows of A. But interestingly, you can also view things from a synthesis perspective. So synthesis, where we're using the elements of x to tell us how to combine the columns of the matrix. So we're using the columns as a basis, as kind of, components that we're then just summing up according to what's in x. So we're synthesizing using the data in x, but using the columns that are available to us in A. So there's kind of a synthesis, there's an analysis perspective, taking a signal and breaking it down, and a synthesizing perspective where you take a bunch of ingredients and you combine them according to the recipe given by your inputs. And we're going to see both of those come up as we go. Okay, let's just look at some example matrices and what they do. So this is kind of the zeros matrix. And what does it do? Well, any input that comes in, it's just going to get set to 0, right? So, let's look at it from the, the analysis perspective, right? Okay, so the first row is 0, 0. We're going to multiply it by x1 and x2. Well, it's just going to produce 0. And the second row, well, it's going to do the exact same thing, right? 0. So no matter what comes in, 0 is going to come out. So now the identity is kind of like, well, opposite maybe is not the right word, but what it does is it just reproduces the input. So let's try that out. So the first row is 1, 0. Well, this is just going to produce x1, right? So the 0 is going to hit x2, it's going to get squashed. So all that left is x1. 0, 1, on the other hand, the first guy is going to get squashed, but the second element will remain. That will stay. Here's the next one we have in this list is the all ones matrix. And what will it do? Well, each one of the elements of y is just going to be the sum of what's in x, right? So we're kind of getting some kind of a dimension reduction here, where both of these elements are becoming the same thing. We're kind of throwing out some information. We had 2 values, but now we're kind of summarizing with 1 value, which is their sum. Uniform scaling is just like the identity, but instead of having 1 there, we put k. So the values are actually blown up by a factor of k. But we can do other things, right? We can actually scale by different amounts. So this is kind of a and b, and now we put in an a there, we put in a b there, and now we scale our inputs differently. So that's kind of a diagonal matrix. We're going to see that when we do talk about SVD. You can do things like permutations. You can do things like rotations, where you take an input and you rotate it by an angle theta. So one way that's kind of nice to see that is by using the synthesis approach. So, let's say we've got cosine theta, sine of theta, and now we're going to multiply it by what does it do to the standard unit vector along the x direction, right? And that just has coordinates like that. Well, if we take the synthesis approach, well, we know the answer is cosine theta sine theta times 1 plus 0 times that. So it's just going to be this. So what has it done? Well, it's taken a unit vector, so E1, and now it's transformed it to cosine theta sine theta. So you can think of it as having done a rotation. Okay, so that's kind of how you can play with some of these and get a sense of what they do. Now, how do we make more complicated transformations? Well, one way is just to combine simple ones, right? So we can just take, let's say we wanted a scaling and a rotation. Well, we first do the rotation, and then we apply the scaling, and then we combine these two, and let's say what it would look like. So we can just do that. So this is going to be a cosine theta minus a sine theta, and it's going to be b sine theta, b cosine theta. So that would be our A matrix. And if we looked at that, we wouldn't immediately see what it meant. But if we kind of stared at it a bit, we'd be like, okay, so it's actually composition of doesn't happen often, but combination of rotation and a scaling. So that's kind of one way of building more complicated transformations out of simpler ones. But we're not always so lucky, right? We're not going to get such transformations that are easy to express. The matrix elements, they could be anything. So how can we understand more complicated matrices? Well, so it turns out now we see singular value decomposition. So before we get that, we found that diagonal matrices were actually quite easy to work with. Right? All they did was they just took the elements, multiplied the top, multiplied the bottom. But what about an arbitrary matrix? Right? It looks quite complicated. Like we have to do this complicated sum. Like what's going on? Now, a really surprising fact, perhaps, is that every matrix is just a composition of just 3 operations. So we can kind of also write these as let's call this the analysis, synthesis, and a scaling. Okay, so what are these operations? What does it all mean? So, turns out the columns of V, so the rows of V transpose, are an orthonormal coordinates, which is a coordinate system for the input space. And the columns of U are a potentially different a different coordinate system. Remember, this could be a completely different output, so there wouldn't even be a question of are they the same coordinate system. They wouldn't be talking about the same spaces in general. But these form a coordinates for the output space. And its diagonal matrix of non-negative, there'll always be non-negative singular values, applies a scaling. So one way to see this is that if we use V coordinates for the input, so if we're living in V coordinates, and we use U coordinates for the output, then A is just a scaling in those coordinates. Okay, so that's kind of one way of thinking about that. Here's kind of a picture from Wikipedia that's kind of describing what's happening. So again, here is this transformation that's happening. So we're getting the inputs, we're transforming them into this shape. Well, we can actually think about it as projecting into our V coordinates, applying a scaling, and then synthesizing back out. So using, wherever we end up as the amount by which we should combine the columns of u, the coordinates of u, to land a point on the output. So we can kind of project, scale, and then project back out. Analyze, scale, synthesize. Maybe I'll write that. Analyze, scale, synthesize. Now, sometimes if the dimensionality of the input and output is the same, then you can think of this analysis and the synthesis steps as rotations. So you can kind of think of their effect will be like rotations. So you can think of what's happening here as a rotation, as they've done, a scaling, and then a rotation back. But in settings where the dimensions aren't, when you have like square, rectangular matrices, then one of these guys isn't going to be square. So then it's not quite as easy to see as a rotation. It's still kind of rotation, but on some subspace it gets kind of complicated. So I just like to think of it as an analysis, a projection, a scaling, and then a synthesis, and that always works. So again, lots of ways to think about it. One thing that happens that I want is good to flag up is that because we can apply this to any matrix, like here's a rectangular one, well then some of these objects aren't going to quite have, they're going to have kind of funny shapes. So actually, I'm not actually a big fan of the way it's come up in this Wikipedia thing. This will, in for example, in SciPy, will come up as a 3x4, so this will be your U. And then you don't have this bottom column, it'll just have a diagonal matrix, that'll be your sigma. And then this will be a 3x3. Okay, so you can think of this as projecting into, you're projecting into the V coordinates, then you're doing a scaling, and then you're using that scaling to combine these columns of U, these coordinates of U, to give you a value on the output. And this final coordinate you just ignore, because you're going from, in this case, from a 3-dimensional space to a 4-dimensional space. So there's going to be one coordinate that you actually can't do anything about. Okay. We're going to apply it now in this particular case to an actual, so again, you can see what's happening. So the very first step, we're going to apply an x, project x onto the input coordinates, right? So this is, again, our analysis step. We're taking x, projecting onto the individual coordinates. In the next step, so this, we're going to scale the result, right? So here's a scaled result. And then finally, we're going to synthesize. So we're going to use those scaled analysis results and use them to combine the columns, give us a position in the output space according to these coordinates. That's another way of thinking about it. Combine the columns, synthesize the position in the output space. Okay, so analysis, scaling, synthesis. Here's some example SVDs of some matrices. So for example, here is the zeros matrix. For the zeros matrix, it doesn't really matter what you pick for V and U, but let's say by convention we'll take the identity. But notice that singular values are 0. So whatever your analysis step does, your scaling is 0. So you get 0 into the final step, and your output is always 0. The identity is very similar, except the singular values are 1. So whatever you project, you just leave as is, and then you project back out in exactly the same way. Okay. The negation is interesting because you can't put negative values on the singular values. So you have to put the negative values on the basis element. So notice that here, this 1, we've got -1. 0, 1, -1. So it's like you project along one direction, maybe this one, and then you analyze along that direction. But then when you project out, you project in the opposite direction. So you're going to project out in that direction. Again, here's, you're going to analyze along 0, 1, don't scale, project out in the opposite direction. The all ones matrix was interesting because it had this kind of dimensionality reduction thing that, both of its rows were doing exactly the same thing. Well, that shows up in one of the singular values being 0. So it's saying that along one dimension, you're actually squishing everything. You're squashing everything. And in the other dimension, well, because you're adding up, you're actually amplifying. Diagonal matrices are very easy because those diagonal amounts just show up here. So and analyze, synthesize the same way, but scale by the diagonal amounts. Here's kind of the permutation matrix, which is another fun one. Again, it's not changing the size of anything, just shuffling things around. And so it just has kind of shuffled inputs and outputs. And the rotation, well, the input, you don't have to do anything on the input side. Again, you're rotating, you're not changing any sizes, you're not amplifying anything. You just end up, your last stage could be a rotation. So that's kind of how you capture. So that's going to give you some example of, what some of these SVDs look like. Now, what were we actually after? Well, we were actually after the variance of pseudo-neurons, right? That's why we went down this SVD route. And we remembered that it was this projection onto the covariance of the direction that defined the pseudo-neuron. So now how can SVD help us maximize this quantity? Well, it turns out that for covariance matrices, the input and output coordinates are the same. And so the covariance matrix acts kind of like an equalizer, like an equalizer for sound. So the inputs are analyzed in V coordinates and scaled, and then they're kind of projected back out along those coordinates. So think of this as, you take your sound wave, you project it along, the base direction, you apply whatever scaling, your volume knob on it, and then you reproduce the base, but with that scaling applied. And then you combine that with the same thing for the next frequency, same thing for the next frequency. So it's kind of a, you figure out how much bass you have in your signal, how much treble, you then scale it by some amount, and then you reproduce treble with the result of that scaling. So it's really acting like an equalizer, kind of an equalizer on your amplifier or your sound system. It's exactly that idea. Now, one thing I just want to touch on is the very close similarity, well, the close connection between SVD and something called the eigen decomposition, because you'll actually hear it. You'll hear these two in very close proximity, and you can kind of compute the eigen decomposition from the SVD, although not always the other way. So as we said, all matrices have SVDs, just like this. But for covariance matrices, we saw there's kind of a special property. The input and output coordinates are the same. So you'll get the covariance of this data. That will actually end up being, turns out, the singular values will be those of the data matrix squared up to the ratio, the division by the number of elements minus 1 or whatever you have to do for the covariance. And notice that it's the same vector, the same kind of coordinate system, but for the covariance, it actually shows up on the input side as well. So this expression is also known as the eigen decomposition of the covariance matrix. Okay, so square matrices have eigen decompositions, and for covariance matrix, it equals its singular value decomposition. And so just kind of pointing out the right singular vectors of the data matrix, these guys are showing up there. And the singular values are closely related. So the singular values of the covariance matrix are also the eigenvalues of the covariance matrix, and they're proportional up to that scaling factor to the squared singular values of the data matrix. So there's just this kind of, so when we talk about variances, often some people will talk about, the squared singular values. So then they're talking about the singular values of the data. But you can talk about singular values of the covariance matrix, but it's just more typical to talk about eigenvalues. So you just have to kind of just remember this, that there's this connection between these two, and just remember what you're talking about. If you want a variance, you kind of think about these S's as standard deviations. So if it's singular values of the data, it'll be standard deviations. If it's singular values of the covariance matrix, also known as eigenvalues, they're going to be the variances. Okay, so just kind of a small point. You can come back to it as needed. All right, so now let's talk about finally, like, how do we use these maximum variance directions from SVD? How do we use SVD to find these maximum variance directions? So it turns out, let's kind of just put in our formula, right? So we've got the direction, the covariance along a particular direction. So it's projecting onto U, and this is our SVD, right? And so all we do is we bring the U on the inside. So U projected onto VI, U projected onto VI. Well, it's the sum of these singular values weighted by those projections. So now the question is, how should we set U to maximize this quantity? Right? So let's have a look. So let's say, let's choose some different colors. So here is V1, a unit vector. Here is V2. And I've just been told that V1 amplifies things by some amount, 10, and V2 shrinks things by some amount, 0.1. So what do we mean? So what do we mean by all this? So let's say I put in, and I can choose, remember, U is a unit vector, so U can live anywhere here. Okay, so let's say I pick U corresponds to V1, so let's say I did that. Well, then U V1, the projection of all of U would go along V1. So that would be 1. There would be none left to go along any other direction. And all we would get in that case would be, let's say this was 10. We'd get 10. So let's mark this. It goes all the way out to 10. Now, as we start moving away, well, we're not going to get 10 anymore, right? Because the amount that we've contributed along V1 is less than 10. And then the amount that's left to contribute to, the other directions, well, those directions are actually they're not providing 10, they're providing some smaller amount. So that the sum that we're going to get is actually going to be less than 10. So until all the way we reach V2, where all the energy is there, and we're getting 0.1. Right? So imagine, you've essentially got, here is V1, and it produces 10. Here is, V2, and it produces 0.1. And now you have to split your data among these directions. So how are you going to do it to get the most energy out? Well, the way to do it is to put all of your energy into V1, right? Because any other way you distribute your energy, the more anything you take out of V1, you have to put somewhere else. And that's going to reduce the amount of energy you can get. Why put your, why put your vector in along a different direction which doesn't produce as much amplification as you can get? So you want to max out the amplification. You put all of your energy, all of your direction aligned with the first principal, I'm already saying it, the first direction, I guess the right singular vector or whatever it is. Which will also be the left singular vector. So you put your U1 to line up with V1. So that's the maximum variance direction. So to get the maximum variance, your input should line up, your pseudo-neuron should line up with the first principal component. Now, or for PCA, we want to get, after we've gotten that one, we want to get what's the next principal component? Well, you get it to line up with V2, right? Because you can no longer line up with V1. You want it to be perpendicular. Well, the next direction that's perpendicular to V1 is V2, and that has the highest, that's whatever's left, the highest of whatever's left, and you can keep going and just reading off the singular vectors from your SVD, from the SVD of the covariance matrix, equivalent the eigen decomposition of the covariance matrix, and read off those directions and produce the best thing you can do while being orthogonal to what you've already chosen. So once you've picked that direction, you can't use it anymore. So in this case, all you have is this direction. Okay, so that's what you'll do. But maybe there's a third dimension in 3D space. Okay, so now this will be your first direction, your first principal direction, your second principal direction, and then your third one. Okay, so that's kind of how it works, and that's how you can read off what these directions are, these maximum variance directions from the SVD. Great. So finally, we can actually do some dimensionality reduction. So the idea is, I should have plotted it here, but the idea is now you plot you mean subtract your data, and then you project it along these directions. Now, I haven't done that here. This is still the original data, but now you can see, okay, now we're back into that PC plot, right? So when we look at we're now no longer looking at the activity of neurons, we're looking at the activity of these pseudo-neurons that correspond to these principal directions we found using SVD. And now you can see that they kind of find this nice kind of splitting, they can split the responses into the into this one set of odors and another set of odors. And you can compare, other pairs of these principal components as well. Looks like there's a split also along, PC2 and PC3. Could be the same one actually. So PC2 seems to really split the odor responses. But we didn't build that in. It just so happens that's kind of in the data. The next best thing, once you've done that, it's very fun to actually look at the principal components that were learned and see, what's going on. And so, for example, we saw this split that's happening, right, of PC2. It's splitting this set of odor responses from this set of responses, the bottom row from the top row, because that's how I colored them. So the blue seem to be up here, the red are down here. And now we can look, so what does PC2 look like? It was PC1 versus PC2. Notice that in PC1, so that's PC2 actually, is the orange one, there's this pseudo-neuron. These are the pseudo-neurons, right? They're combinations of the real neurons. And this one says that, PC2, pseudo-neuron 2, has lots of activity for this batch of neurons. The x-axes are aligned here. Whereas PC1 doesn't have very much. So PC2 seems to be kind of particularly, this early part seems to be quite similar for all of them. But PC2 seems to pick out activity along this particular, one of the things it does is pick out activity along this set of neurons. And so indeed we see that if you did that, well, you find that, okay, they don't respond very much to this group, but they actually do respond very much to this kind of this bottom set of odors. And that potentially explains the split that we're seeing. So again, so naturally, without we just pick directions that had kind of the most variance, but those directions are kind of informative about what's going on in our data. We don't have to look at whack combinations of pairs of neurons. We can just look at these principal components that capture most of the action, and sometimes we can actually see interesting features of our data. Another nice aspect is that we can use those singular values, the variances along each direction, to measure dimensionality. So we can use this, and the way we do that is we kind of normalize. We take the sum of the variances, the squared sum, and we divide by the sum of the squares. And to kind of give you some intuition for how that works, why it gives the right answer, imagine a couple of extremes, right? Like imagine this particular extreme, where all of the energy seems to be, let's say, mostly along one direction. So in that case, what you will get, your S's looks like, basically 1 and then some small amount. So this sum at the top, oh, you guys can't see. So let's just do that again. So in this particular case, imagine, and that's how I actually built it. So S is equal to, some large amount corresponding to this direction, and then maybe some small amount. Well, then if we compute the sum, the top, we'll just get, sum on SI is basically equal to 1, and the sum of SI squared is basically equal to 1. And if you take the ratio, you get something very small. So it just says, most of your energy is there. There's only 2 principal components. So this is kind of a 2-dimensional. This is a basically one-dimensional data set. On the other hand, over here, the values are about equally spaced, equally distributed. So let's say what would happen if they were equally distributed? Well, we would get in that case, let's just call it S over sum on S squared. Okay, so this would give us this should be sum on S squared. So this would be ds squared over d s squared, right? And so then this is going to be let's move this out of the way. This is d squared s squared over ds squared. And so these cancel out, and you get d. You get the dimensionality of your data. So we have these kind of two extremes, right? When the data is kind of very, very much along one dimension, you get 1. When it's kind of evenly spread out, you get whatever dimensionality of your space is. So it's kind of a very useful way of estimating dimensionality. One definition of it just measures, how concentrated the energy in your data is. Another very useful application, which we'll just touch on, is using those first components to approximate your data set. And the basic idea there is to approximate, your population response, your population vector. Take the first, 1, 2, k components, and keep those projections exactly. So we're going to take this. Remember, we have an orthonormal coordinate system, so we can describe this by analyzing it into all of its components, onto all d directions, and then synthesizing it. But we're going to do that just for the first k. So we're going to the first k direction. Think of it as keeping the first 5 most informative directions, and the other directions you're going to approximate using the mean, the projection of the mean. So here you use the exact value for the first k, the actual value, and for all the rest you use the mean. And so that's your approximation. It's kind of a k component approximation. You're going to throw away the rest of the data, just replace it with the mean. Another way to view it is that you're approximating your data point as the mean, but then for the first k, along the first k directions, you allow having a component-specific deviation. So you can kind of fill in some details. So you approximate everything by the mean plus some details along the first k dimension. So it's kind of 2 equivalent views of this approximation. And so here's kind of an example of it coming from Bishop, where you've got this original image. I think this actually is the mean for this data set. And then when you use 10 components, you start, you're trying to reconstruct this. If you use all 750 components, you would get this back exactly, because you wouldn't be approximating anything. You would actually just be using the exact values for the entire, for all of the components. But if you even after 10, it's looking pretty good. And by 250, which is about a third of the way to using all the components, you actually get a very good reconstruction. So that's kind of where, this kind of using PCA for approximation comes in. You kind of assume that maybe the low variance components are actually just noise. So you just keep the top components. And it might not be, but that's what you do. Here it is, we're applying it to our data. I've changed the color scheme a bit, but you can see already with 5 components, we're getting quite a good similarity to the original data. Now, how do we decide how many dimensions to keep? And this is kind of there's no good answer for it, but we can kind of use the singular values to kind of give us a heuristic. And you can think of, the explained variance. So after k components, you can say, if I keep the first k components, how much of the total variance will I have kept? So you just sum up the variances that you have, divide by the total variance. Okay, so here's kind of a plot of that for our neural data. So we can see, okay, the first component has a lot of variance, and then it kind of drops dramatically. So some people will say, look, we're going to look at like elbows in this plot. But we can also do it by explained variance. We can just kind of form this cumulative sum of the variance, the scale by the total variance, and say, look, I'm going to keep as many components so that my explained variance is, 90%. Again, the number is just up to you. It can also be like, if you're visualizing your data along 2 dimensions, you say, well, I'm visualizing along 2 dimensions, and that captures 70% of the variance. So maybe, sometimes it doesn't capture so much. But you say, look, captures maybe more than half of what's going on. So this picture you're seeing here is actually, maybe it's accurate. But again, it's going to be a heuristic thing. It's just a measure that you can use to see how well you're doing when you're doing this approximation, or when you're doing the denoising. Like, how much of the variance have you left on the table when you approximate with like the first 2 components. Awesome. Okay, so let's just look at, we're going to just briefly talk about a few adjacent approaches that you should know about. That come up in different situations, related but not the same as in PCA. So the first one is kind of exploiting nonlinearity. This is pretty cool. So PCA it turns out you can express PCA in terms of a similarity, a notion of similarity between the data points. Now PCA uses linear similarity, so it's kind of two of your population vectors are similar by the amount they kind of overlap on top of each other, by their projection onto each other. But there's a notion, something called kernel PCA, which generalizes this and allow you to use other similarity measures. And now why might you want to do that? Well, again, let's go back to the Swiss roll situation. So the point is that maybe the distance between, the similarity between 2 points, here's kind of the Euclidean similarity, kind of this overlap, would be something like this. Well, maybe the one that's actually relevant is not the distance kind of in Euclidean space, but this distance along the manifold, right? So it's kind of a nonlinear distance. You actually compute, and the way they do it is they form this nearest neighbor map to estimate the geodesic distance, the distance on the manifold between 2 points. So, for example, these two guys who are very similar in Euclidean space, so, as far as PCA is concerned, they'd be considered very similar. Well, we actually want them to be put very far apart. And so kernel PCA is a generalization of PCA which allows you to do that, which is pretty cool. So you can kind of think of it as you're doing basically the same thing, but with a nonlinear similarity metric. Another way to think about it, with these kernel methods, the kernels correspond to features in some kind of high dimensional, sometimes infinite dimensional feature space. So an equivalent way to think about this is as projecting your data into the feature space and then doing PCA there. So that's kind of another perspective. But it's just something to know about, a way to take advantage of nonlinearity. Now, what if you have kind of different data sets? So PCA is kind of finding variance directions in one data set. You can imagine it as finding directions with which have high covariability with themselves. What's variance? It's like covariance of something with itself, right? So PCA is finding directions that have high covariance with themselves. Now, what if you have two data sets? Well, it's kind of very natural to consider one direction from one data set, another direction in another data set, where those projections have high covariance. And that's actually quite useful. So for example, here's this odor response data set we've been playing with so far. And here's a response in another area, kind of the output of the structure we're interested in. Here's the input and here's the output. And look, they have different numbers of neurons, so we can't, they're just different structures, so we can't compare the neurons. But what we can do is we can look for projections against a pseudo direction in this space and a pseudo direction in that space, where if you project the data onto those directions, there's high covariability. There's high, for each of these odors, right? So we can look at, I'm going to pick a pseudo neuron here. It's going to have 48 odor responses. I'm going to pick a pseudo neuron here. It's going to have 48 odor responses. I'm going to then compare those. And so CCA essentially allows me to kind of find these directions that have covariability across different data sets. And you can do things like, for example, plot them just like before, and you can actually plot, you can kind of verify that. So here was the response of, the pseudoneuron from one area, the pseudoneuron from the first pseudoneuron from the other area. You can see indeed they're actually quite correlated. So there's some kind of connection about the transformation going on from one area to the next that's producing this correlation. The pseudoneurons it gives you, just like in PCA, form a basis of the corresponding spaces. So you can still do, within one space, do your PCA analysis. But note that those directions are now not going to be necessarily the PCA direction. It's going to be some other basis that is going to produce high covariability across data sets. So this is just a technique to know about if you're comparing data sets, which as neuroscientists you will often be doing. And finally, so what if we have labeled data? So everything we've been talking about is kind of unsupervised, right? We have some data points, there are no class labels. And so we thought, okay, we should maximize variance. Now, if you have data that you want to discriminate, then maximizing variance is often not the best thing to do. And so here's a great example of this from Bishop. So here you have, let's say, neuron 1, neuron 2. Let's just label them. So they're not really neurons, but let's just pretend they are. And now we have these class labels, right? So if we were just doing PCA, we would ignore the labels and we say, let's find the direction where if you project the data along it, so a line where we project along it, we get the most variance, right? And so you can see that most of the action seems to be this way. So this line seems pretty good, right? So if we project onto this line, then most of the variance is going to be captured. There isn't that much in this direction. But that's not what we want to do in this setting, right? We have labels, so we want to actually find a direction where that discriminates the data the most. And that direction actually turns out the one, in this case, which actually almost has the least variance, right? But variance is not what we care about here. We care about separating these groups. So if we project onto this line, well, then we're going to get a big clump here and a big clump here. And they're going to be separated. So this is kind of an example of where maximizing variance is not what you want to do. You want to maximize discriminability. So when you have labeled data, kind of the related approach to use isn't quite PCA, it's LDA, linear discriminant analysis. It finds linear directions in your space that best discriminate your points. So it doesn't care so much about variance, but about discriminating the two groups. Okay, so you should just know about those because this just comes up all the time. PCA isn't always the thing you want to do, and different situations will call for different tools. Okay, so finally we're here at the summary. So we covered kind of a lot of ground. Neural data that arrive in single neuron coordinates that we talked about. But other coordinates might be more informative about the data, and PCA finds coordinates that capture the most variance. And how do we find those coordinates? Well, we can use SVD to find them, and we can use it for dimension reduction, visualization, approximation, denoising, all sorts of other things. And there are many extensions. So I think PCA is kind of in some ways, an entry point to this big, very interesting world of dimensionality reduction, manifold learning, etc. And some of the really important ones are Kernel PCA exploiting nonlinearity, CCA for comparing data sets, and LDA for when you're dealing with labeled data. So I think that's about it. Hopefully that was useful, some interesting perspectives there. I hope that helps with your analyses, gives you some insight into PCA, and helps you understand neural data or whatever data sets you're working with. And thanks for listening.